Next, exercise 7. In this one, we have to prove this proposition 8, 1, 10, and its statement is just this: two sets x and y are given which are both countable. We need to prove that their union is countable, and we can see that there is an elaborate hint that is also given, and which is actually just the solution itself. So because it's given that both x and y are countable, so there would be bijections like this f and g from the set of natural numbers onto these sets. Now these bijections then should be used to set up a function h from n into x union y, and then in fact this function, and we are also going to use this function. We will then have to show that the image of the domain under the function is the range itself, x union y. In other words, we need to show that this h is an onto function, as adjective function. And then we have to use corollary 819, which states that for any such function where the domain is the set of natural numbers, the image set is at most countable. That means x union y would then be at most countable, and then along with that, if we are also able to show that x union y cannot be finite, then it has to be countable, because by then it will have been proved that it's at most countable. So combining that with finite with infiniteness of x union y, it would then imply that x union y is countable, and that's what we want to prove. So let's see the solution. So we start accordingly, since x and y are countable, so such bijections exist. There exist bijections f from n to x and g from n into y. We define the function h from n into x union y by the following formula. H of n, in the original hint, it's given slightly differently. That is, h of a positive, h of an even input has been defined separately, and h of an odd input has been defined separately. Here, however, we are not going to take 2n or 2n plus 1, so we are just simply going to take n as a even natural number. Now, depending on whether n is even or not, we are now going to define it. So here, in place of 2n or 2n plus 1, we are taking n. So the formula, that is, this will look slightly different. So it is this. It is f of n divided by 2 if n is even, and g of n minus 1 divided by 2 if n is odd. But despite this difference in their look, actually this h is just that one itself. You can see for yourself. But we need not worry about whether this matches with the hint or not. All we now need to show is that this h is an onto function. It maps n onto x union y. But before we do anything with h, we need to first of all make sure that h is a well-defined map. And for that I am just simply going to write clearly h is well defined. Now is it really clear? Let us see. What do we need for well definedness? You take any natural number, its image under h should first of all be an element in the range. That means it should be in x union y. And the second thing is that for that given input, the output should be unique. There should be only one output. If these two criteria are met, then only h is well defined. That means h is a legitimate function, and then we can work with it. Is it the case here? Let us see. So say we have chosen an input n. So n is either even or odd, and of course not both simultaneously. Say n is even, okay, then n divided by 2, it is itself a natural number, and we are defining in that case h of n to be the f image of n divided by 2, because f itself is a well-defined function from n to x. This is unique. For a given n, this is a unique element where in x and hence in x union y. So there is no problem if n is even. What happens if n is odd? If n is odd, then n minus 1 divided by 2 is a unique natural number. How is n minus 1 by 2 a natural number? Because then n minus 1 is even, so n minus 1 divided by 2 is an integer. That much we can say. But at the same time, because the smallest odd natural number is 1, so in general for an odd n we have this inequality. N cannot be 0 because 0 is even. So this implies that n minus 1 is a non-negative natural number, and which due to the oddness of n is now even. N minus 1 is even. So that is why n minus 1 divided by 2 is an integer that is non-negative. That means it's a natural number. And for a given n, this is unique. So its own image under G will also be unique, because just like f, G is a well-defined function from n to y, and this output, final output, will belong to y, and hence also it is in x union y. So that is why in both the cases for a given input there exists a unique output in x union y. That is why h is well defined. Okay. Now we need to show that our function h is onto. That means surjective. For that we will choose any element in the range and show that that element is the output of some input under h. So let x be an element in the union. Okay, that means x is either in x or in y. It may be in both also, but we need not consider that. If x belongs to x, then x is equal to f of n for some natural number n, and this is because f is onto, being a bijection, f is onto, so our x is coming from x, so it should be the output for some input n under f. So in brackets we write, since f is onto, but then x is equal to f of n, which can also be written as f of 2n divided by 2. Now note that because n is a natural number, that means a non-negative integer, 2n is an even natural number. So that is why from the definition of h, this is h of 2n. So we have realized x as an h image where the input is 2n. On the other hand, if x belongs to y, then we do a similar thing with g, like this. Then x is equal to g of m for some natural number m, again since g is onto, just like f. Let me keep this function definition. Since g is onto, but then x is g of m. Now note that g of m can be written as g of 2m plus 1 minus 1 divided by 2, because this is just m. Okay. Now just like that previous case, because m is a natural number, 2m plus 1 is also a natural number, but it is odd, and that is why from the definition of h, this becomes equal to h of 2m plus 1. So in this case also we have realized x as an output under h with this input. So h is onto, and as a result h of n is x union y. And now we invoke corollary 819, it was, no? Yeah, to claim that x union y is at most countable because it is h of n for some function h. So by corollary 819, x union y is at most countable. Okay, now in order to claim, not in order to conclude that x union y is actually countable, we need to show that it is infinite. If we suppose that x union y is finite, contrary to what we want to show, we suppose that it's finite. Then x is finite by one of the properties of finite sets, which says that any subset of a finite set is also finite. But this contradicts the hypothesis that x is countable. And exactly why is this a contradiction? It is because you see, what does countability mean? Countability means that there is a bijection between x and the set of natural numbers. Now, if we also have that x is finite, then there is a bijection between x and a finite set. And using these two bijections, we will then have a bijection between the set of natural numbers and a finite set, proving that the set of natural numbers is finite, which it is not. We have already proved that n is not finite. In fact, way back in the section on finite sets, I think 3.6, there itself we showed that the set of natural numbers is not finite. So that is contradicted. So that is why our supposition is wrong. So the above supposition must be wrong. But then x union y is at most countable, and also it cannot be finite, it has to be infinite, then it must be countable. Hence this is, I'm just directly writing the final conclusion. If you want, you can stretch it a bit more by writing that the supposition is wrong, hence x union y has to be infinite, and as a result it should be countable. So this completes the solution and the proof also. So let us now see the next one. So do you see one technique of proving that some set is countable? You set up a function between that set and the set of natural numbers and show that that set, that function is onto surjective. That is one thing. And then you show that your original set, which you want to prove is countable, is infinite. Then this way you can show that it is countable. So why I am saying this? It is because it is not necessary to set up a bijection between your given set and the set of natural numbers. Finding an onto function is much easier than finding a bijective function, because bijection requires that the function be onto as well as injective. So that is more requirement, but this way we can get it done much more easily. Okay, now the next one. Use Corollary 8.1, 13 to prove Corollary 8.1, 14. Just a moment. Okay, let me first of all clean this part. Corollary 8.1.13 is that statement which says that the Cartesian product of the set of natural numbers with itself is countable. And in Corollary 8.1.14 we have a general version of this where we have, in place of n and n, we have two countable sets x and y. Then their Cartesian product x, Cartesian product y is also countable. That is this corollary that we now need to prove. Okay, so that means what we are given in this corollary is we are given two countable sets x and y. We need to prove that their Cartesian product is countable. So we start like this, since x and y, just like before, are countable, there exist bijections f and g. Okay. Now in this case we again we will set up a function, but now not between x cross y and n, but between x cross y and n cross n, because that's much easier. Now define this function h by this extremely natural formula. F of n comma g of n. Let's now look at this formula. Again, we need to see, whenever we define some function, it's from our side, we need to first of all make sure that it's actually a legitimate function. That means it is well defined. So like before, so say this is your input. Input is an ordered pair of natural numbers n comma n. Does the output first of all belong to the range, the second set? And the second thing is that, is the output unique for the given input? In this case, it's easy to see both of them at once. So n and n comma m is given means this ordered pair uniquely determines its first coordinate as well as second coordinate. If an ordered pair is given, then it has only one first coordinate and one second coordinate. So that means n and m are uniquely given. Fine. Then because f and g are themselves well defined functions, so f of n is a unique element in x, like that g of m is a unique element in y. So that means this is a unique ordered pair in x cross y. So that is why h is well defined. In most of the cases it's almost this easy, but sometimes especially in algebra where we deal with say cosets or ideals or things like that, some functions, I mean, it's not that apparent that once you define a function, immediately one can see that it's well defined. It needs some work, some effort, but here it's quite straightforward. Okay, now we just need to show that this H is actually a bijection. That is also extremely straightforward, but still let's go through it. So for bijection, for showing that H is a bijection, let us first show that H is an injection, an injective function, one-to-one. So we take two inputs and such that the corresponding outputs are equal. Okay, then let us write it as an equation array. That way the writing will be minimal. Then this equation just simply means f of n1 comma g of n m1 2, many things are there, I should not make mistake. F of n2 comma g of m2. Okay, this implies what? Two ordered pairs are equal if and only if their corresponding coordinates are equal. That means this is equal to f of n2 and g of m1 is equal to g of m2, and this implies n1 is equal to n2 and m1 is equal to m2. Why? Since f and g are themselves injective because they themselves are one-to-one functions, and this then implies that the ordered pair n1 comma m1 is equal to the ordered pair n2 comma m2. So having assumed that the outputs are equal, we have shown that the inputs are equal. That means H is injective. So H is injective. Next we want to prove that H is surjective. So for that we are going to choose an element here and show that it is an output for some input. I think you can almost see how we are going to proceed because of the straightforwardness of the situation. Next, let this ordered pair be chosen from the Cartesian product. Then x belongs to x and y belongs to y. Since f and g are onto, that means surjective, so x is equal to f of n and y is equal to g of m for some natural numbers m and n and m. But then what? Then our ordered pair becomes f of n comma g of m, and that just simply is the H image of n comma m, where the ordered pair n comma m of course comes from the Cartesian product n cross n. So this shows that any element in x cross y is an output for some input in n cross n, and so H is onto. Thus H is onto. Now being one-to-one and onto, H is thus bijective. It's a bijection. So H, this is a bijection. Now we invoke this previous result, corollary 8.1.13. By that corollary, this is countable. Oh, what have I written? I did not complete this. No? This from n cross n to x cross y. This function is a bijection. Now by eight one 13, the domain of H is countable. Hence, this Cartesian product is also countable, because using this bijection H and a bijection that will exist between this set and the set of natural numbers, you can set up a bijection between the set of natural numbers and this Cartesian product, proving that it's countable. Using these two functions means you have to take their composition. So this completes the solution and also it proves this corollary. And this is where I end also today's video. Two more problems are there in this set of exercises. Once they are over, we can then move on to the next section. Sums on infinite sets. We will see what it means, how we can take sums of the elements in an infinite set, and how then it can be used to ultimately prove that the set of real numbers is uncountable. That is still there. We have not proved it yet in this text, so we will see how that can be used successfully. So that's just it, and the next video is of course this coming Tuesday, and on Tuesday we are going to see graph theory again. So I wrap things up here itself. So see you on Tuesday with graph theory. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.